All right, we're recording. So this is AP Physics, day 2, doing Wednesday, August 11th. Yesterday I had a day 1 presentation that, ended up I only got about halfway through what I wanted to talk about. Talked a lot about, you guys figuring out what your interest is going to be. I know you guys are AP students, so usually pretty on top of things, pretty motivated. Help you guys with organization planners, that sort of thing. And what else I wanted to do, and what we're going to do today, is I want to throw a bunch of physics questions to you guys. Just talk a little bit about physics, just so you can get a survey of the class, have an idea of what kinds of questions that you would be addressing and running into. Okay. Now, I know being probably, ready to get some notes, but, ready to jump into the first few topics, but don't worry, we got time. We're going to do everything. We're right on schedule. Everything I want to do. So let me give you guys an idea of what we're doing next few days, next few weeks, what the schedule's going to be, so you guys know we're going to be good. Okay. So today, like I said, I'm going to throw a bunch of questions at you guys, just get you guys thinking about these things. I want to do my best not to reveal a bunch of answers to you. Talk about a few of these demos. The tail end of today, I want to throw a little bit about vectors at you guys. You guys might remember a little bit of trigonometry, so just refresh that. Okay. The next couple of days, I'm going to do a hands-on project that involves paper and glue. Now, there's reasons for that. Talk about tomorrow, but actually, I'll tell you guys right now. So one thing that will help me do is there's a project I like to do right at the beginning of class, or right at the beginning of the year. That on my end, it helps me because I can have the sitting chart that I just put together and learn your guys' names. So I want to do that. But on your end, what's going to do is see, when you're working with paper and glue, we're going to put together like things that move, like have mechanical motion of parts. Is hopefully awaken the part of your brain that involves thinking in spatial dimensions, like 3 dimensions, looking at putting things together, how do things interact. Yeah, I found that over the years to be a really good beginning of your project. We'll do that. Then next week we're going to have a bunch of interesting stuff related to this class. So I definitely want to talk about vectors more. Do some trigonometry and vectors and vector components. You guys might see in class, got this poster up here. So pretty much that, just stuff related to that. Some beginning type assignments labs. Review with you guys the metric system, which we're going to use in this class. So we're going to be measuring in like meters and kilograms, not pounds and feet, that sort of thing. So metric system, precision, accuracy, scientific notation, maybe a little bit of an algebra view. You guys are probably pretty good on algebra, but there's my other classes want to go that. So we'll hit all that stuff, make sure you guys have a really good solid foundation. And then the week after that, so it's a couple weeks from now, we'll actually get into linear motion, which is the first AP topic. But we're going to get there, we're on track. This is we're exactly where we need to be. Okay? So question for you guys here is, before that, we read that. So physics, this is my own definition, but I think this works pretty good. Studies of the laws of nature that govern matter and motion in the universe. Yeah, that's what you guys are learning in this class. Yeah, so that by the time AP exam rolls around, you will have mastered the rules of the universe, how things move and work. The question that goes with us is, that picture on the background, does anybody know what picture that is? That's a really famous picture. Yeah, go ahead. There's the Hubble Big Did I talk about this yesterday? Yeah. Oh, okay, so I did talk about that. Yeah. Right, so they had to leave the camera exposure open for like several weeks to grab light information from that. I had no idea what they're going to get this. Did I tell you guys about the edge of the observable universe? Okay, a little bit? Okay. Yeah, so probably bells ringing right about that, I'm guessing. So, because of two things coupled together, one, the fact that there's universal expansion. The universe expands in such a way that there's something called cosmological principle. No matter where you're standing in the universe, it looks like everything's moving away from you equal speed, or well, further away, faster it goes. Combine that with the fact that there is a cosmic speed limit of the speed of light, that nothing can move through space faster than the speed of light. Right? Two and two together means that there are almost certainly galaxies behind these galaxies that the light from them will never reach us because they're moving away from us. The space between us and them is expanding faster than the speed of light. It's a really weird concept, but yeah, how that works. So, okay, next slide then. All right, so these next few slides, I'm going to hit topic by topic. Just a bunch of questions, you guys, that want you guys to ponder and think about, and then we'll eventually hit these as the year goes on. So some of the first stuff we'll be doing is vectors. Now, there are lots of different kinds of quantities that we're dealing with in this class. Give you guys some definitions, whatnot next week too. Some quantities don't really have a direction associated with them, or the direction isn't really important. For example, mass, like how massive are you? Like how much matter are you made of? How much inertia do you have? Like resistance to change motion. That does not have a direction associated with it. But a similar concept that does is weight, right? You think you're being pulled straight down? That's like a force, weight. Now, weight is related to mass, but it's a different concept. Talk about that next couple weeks. A different kind of vector could be velocity. That's what you guys are seeing right here. So you got three planes, and I'm representing their speeds with these velocity vectors. So velocity, think speed, how fast, but also do the direction associated with it. So maybe like north in this case, or going north. Okay? Identical planes, they can all apply the same speed. Okay. The plane on the far left maybe is getting a boost from the wind. There's a wind headed in the same direction as the plane. Okay. Now, do you guys think that relative to the ground, that plane on the far left is moving faster than the other planes? That kind of makes sense. It would be, right? So when we're talking about velocity, this is a key concept in this class, especially when we get into kinematic motion. Velocities are always relative to something. All motion is relative. Okay? So maybe the plane velocity itself would kind of be relative to the surrounding air. That kind of makes sense, right? Maybe the jet engines are moving the plane relative to the surrounding air, something like that. And this wind velocity is maybe like the surrounding air moving relative to the ground. Hey, you know what you do? If you put two and two together and get the plane velocity relative to the ground, that would be a different vector, wouldn't it? That's called the resultant. Okay? Now notice how I lined up these original two vectors. Plane relative to air, air relative to ground. Okay. See how I lined up what's called tip to tail, where the tail of this vector is lined at the tip of this one? Okay. And then that gives me this resultant. I can go from the tail of the very first vector to the tip of the very last one. I've got two vectors up here, but if I have like 10 vectors, I could just do the same thing. Okay? And they figure out, ooh, this plane would be moving very fast compared to the ground because it's a very long aerial. And so something about magnitude that's velocity is called speed. Okay? The second plane, well, maybe it's fighting the wind. Okay? Do you think if the second plane is fighting the wind, it's going really slow relative to the ground? Yeah, apply your tip to tail principle. The resultant would be, hey, that little guy right there. Do you think the wind velocity was exactly matching the plane velocity? Do you think that plane would just be kind of hovering there, like a helicopter? Huh, that kind of makes sense. It would be, right? Right now, question I'm going to throw at you guys here. Not going to answer yet, but you guys think about this for a while. Probably get the answer in a couple weeks. Is what if you have a plane in a crosswind, like that plane on the right? So the plane's pointed north, headed north, but it's in the wind that's going straight east. It's not really pushing it forward, and it's not really pushing it back either. Is this third plane moving? Well, I guess there's a couple questions we can ask. As what direction it's going? You can also ask, how fast is it going relative to the ground? Say you're down on the ground, you point your radar gun up at the plane. Okay? How would that be compared to no wind? Huh. What if you guys can figure that out? Think about that. Linear motion. Also, a bunch of these slides, you guys see, I'll put the corresponding AP unit attached it here. So AP unit 1, kinematic motion. Kinematic motion just means motion not considering forces that might be involved in getting it to move in the first place. We're just looking at like the pure motion itself. Okay. So suppose you are in the passenger seat of a car. Your friend's driving, you guys are going up I-95. Right? You're blindfolded. Can you feel whether the car is going 50 miles an hour or 60 miles an hour or 70 miles an hour? Can you feel an absolute speed like that? Is that something you can feel? Huh. Yeah, I hear a lot of you guys say no. Right? That makes sense, right? Or more extreme example, you're in a plane and the plane windows are closed. Can you feel how fast that plane is going relative to the ground? Huh. Seems like no, right? But you can't feel something in the car, right? You get that thing moving and I bet there are certain features about the car you can feel, but maybe it's not speed, maybe it's something else. Huh, wonder what that would be, and how that corresponds to something like speed. Huh. How about this? After we get finished linear motion, we'll take this into two dimensions. So this could be, for example, projectiles could be two dimensions, right? You have an up and down aspect, you have a side-to-side aspect. I bet vectors can be really important by the time we get to this, right? And notice this is still unit 1 kinematic motion in AP's book, just so you know. But here's a fun question, is what is the optimal launch angle to send a ball the furthest distance? So you're out in a big field, you're in a baseball throwing contest with your friends, who could throw the baseball furthest. Now, a variable you don't really have control over is how fast, what is your maximum throwing speed? I mean, it is whatever it is, you throw it however fast you throw. What you do have control over is the launch angle, right? You can throw it pretty horizontal, you can throw it pretty vertical, somewhere in the middle, and somebody's going to be able to send this ball the furthest distance. I wonder what angle you would have to send it furthest distance. Right. I wanted to sketch up a graph for you guys real fast. Okay, so you guys got a pretty good look at that visual, right? Okay. So let's make a graph out of this. Let's say I've got different angles. I'm going to use this Greek letter theta to represent angles, and the unit of measurement is going to be degrees. Okay. When we get to rotation motion, we might switch over to radians for a little bit. But, okay. And then maybe I'll say distance, like maximum distance. Now in this class, I'm going to use x. You guys, if you saw that variables map from yesterday, one of the pages I gave you, right? This could be in meters, right? Because we're going to be using metric systems in this class, so I'll be used to that. I could throw this ball anywhere between 0 degrees and 90 degrees relative to the horizontal. No, I have to specify degrees relative to what? Let's say relative to the horizontal, like the ground, right? So this would be throw it straight forward. This would be throw it straight up, right? Throw it straight up, 90 degrees relative. Now, if I throw it straight forward, it's probably not going to go very far before it just like crashes, especially from like at ground level. If I throw it straight up, it's just going to come and land on my head. Gone basically nowhere, right? Like 0 meters. But if I pitch it out somewhere in the middle, say like 30, 60 degrees, 30 degrees, 60 degrees, 90 degrees, just equally spaced, right? You think maybe pitch out pretty far and probably make a curve that looks something kind of like that? Kind of makes sense, right? So now I've got distance as a function of angle, right? And if I'm really interested in this point right here, what is, I'll call it x max, right? There is some optimal angle, and I may or may not have drawn this curve correctly. I'll let you guys think about that. I'll call it theta optimal. That corresponds to this x max. I wonder what that would be. Okay? Now, different perspectives you could have on this, different approaches. The scientific approach would be actually go out in the field and do this, and launch a bunch of balls at different angles, and make a graph and do something like this, and figure out this point. Right? There's a mathematical approach that I really like a lot, and this is really maybe something you'd see more in a math class. But the reason I want to bring this up, let me see again. Show of hands. How many guys are taking calculus? Okay. Yeah, about half the class. Right, awesome. If you aren't, that's okay. But the reason I want to talk about this a bit is because there actually is a calculus concept here. When I flip the screen back eventually, if you read that question, it says, what is the optimal angle to send the furthest distance, right? Whenever you see the word optimal or optimization, the branch of math to solve optimization problems is calculus, and I'll show you guys why. Okay? Remember yesterday I was telling you guys calculus is about rates of change? Now, rates of change on a graph are like these, what mathematicians would call tangent lines to the graph, right? They're like instantaneous rates of change, right? See how like you can hold like flush up to the curve, it gets shallower and shallower, right? And at this very special point here that I'm really interested in, at the very top, what is the slope of this tangent line? What's the slope? 0, right? It's like, right? Whenever you set the slope equal to 0, normally you're optimizing something. Okay, so just so you know, if you're taking calculus, then look for that. Okay, that word optimal. I'll probably take you guys through the proof one day, but that'll be a fun adventure. Let's talk about forces and laws of motion. Good question. How much fuel does, say, the Voyager 1 and Voyager 2 spacecraft need to keep going? These were spacecraft that were launched back in the 1970s. There's actually a really special window in time when they launched these that the planets happened to be aligned in such a way. I'm not going to cut off a little bit here, but this picture of Jupiter that that it could not only visit all these outer gas giant planets to take pictures of them, but also it could use the gravitational effects to slingshot it, so they didn't need as much fuel to launch them in the first place. Okay? These things have just been going, and well, depending on who you talk to, have maybe left the solar system by now. Then the question is like, well, where exactly does the solar system end? Right? Is there like some area? Okay? But they've been going for decades and decades. No gas stations out in space, so what's keeping it going? Right? For that matter, what's keeping the Earth going around the sun? Why does it just like slow down and come to a stop? Okay? Or maybe if there was some kind of speeding up or slowing down, maybe that would be like a change in state of motion, and maybe there would have to be something causing that. Maybe just you're on the third floor of the building, looking straight down, and on the sidewalk, you see a glass of water. You think, I'm thirsty, I want that water. So you pull out your very long drinking straw, and stick it down there, and something out of a Looney Tunes cartoon, and you start drawing out this water. I wonder if there's like some maximum length of straw that would even work. Or how does a straw work? What are the physics principles involved in that? Because if you know that, maybe you can tackle that question. Back in the day, towns that were sitting on top of hills had this problem. Maybe there was a lake way down at the bottom of the hill, and some of the first pumps were being invented. They started pumping up water, but maybe there's like some limitations, or you can't pump it above like some sort of level. Does it have something to do with gravity pull? Would that be very planet per planet? Does it have something to do with maybe the atmosphere we're in? Maybe something with pressure? Huh. How about this? It's got chopped out again. Okay, so there's a little bit more in this picture at the bottom. Have you guys use your imaginations? Okay. You guys see a little bit of something spherical on the left? It's supposed to be the Earth, right? And then on the far right side of the screen, there's a little dot that's the moon, and basically the width of that screen right there, if you can fill in where the Earth would be, that's the distance between the Earth and the moon to scale. Okay, the Earth and the moon. Okay. Now, does the Earth pull on the moon? Is there gravity pull? Yeah, okay. That's the connection that Isaac Newton made, by the way, when he was watching apples fall from trees, look up in the sky, sees the moon, realized he's maybe the first person in history, at least to write it down, to make that connection like, that's the same phenomenon. Okay? Does the moon pull on the Earth?
Yeah.
Okay. Yeah, you have tides, right? Yeah. Here's the kicker question. Which force is bigger, the Earth pulling on the moon or the moon pulling on the Earth? How many guys say, just got reaction, we'll talk about this later. How many guys think that the force is stronger than the Earth pulling the moon? Who says that's the stronger force, the Earth pulling the moon? Who thinks that the moon pulling the Earth is the stronger force? Nobody say that. But does anybody think that they're the exact same magnitude? Anybody think they're the same force? Huh. Hey, got a few hands there. Right? You guys ever heard a phrase, perfect force is an equal amounts to reactive force? Huh. How would that even work? I answer that one. Might be giving away too much. Okay. Energy. Here's a fun energy question, or energy related. Can water flow uphill? Okay, so got some examples here. This might not be the best picture example. Kind of hard to find these. This is called hydraulic jump. It is a real thing though. I know it's got an animation version down here. You can actually create a hydraulic jump in your own sink basin. Just let the water run right around the sink, like right around this area. If you think the water level is really low, and then this water level goes a little bit deeper, so the water actually has to jump up a little bit. It's a tiny, tiny hydraulic jump right there. Something like that. Okay. There's better examples out in nature too. But this is not something you would typically see. I mean, things tend to want to roll downhill, water wants to flow downhill. If you saw something counter to that, I wonder if there's something special going on here. Is this an exception to some rule? What are the physics principles involved? And I'll tell you what too, when I was your guys' age, like sitting in a physics classroom, this is one of those things that definitely would have lit my brain, because one thing that I was really super interested in when I was back in high school was, could you do something like this? Could you take this deep water level, which is downstream, right, route it around in a loop, and maybe have it fall back down, maybe dam it up with a hydroelectric dam? You know how a hydroelectric dam works, right? You got some deep water, it flows downhill, spin some turbines, capture the energy from it, and you get a good amount of energy from that. Hey, if you could do that, you just keep going through this hydraulic jump over and over, could you get infinite energy from that? Could you create a power plant with no energy input? That might be called a perpetual motion machine. Right? Is that possible? Could you build something like that? Back when, again, when I was about your guys' age, in my room I had, a bunch of stuff like that, a bunch of little like balls and sticks and glue and magnets, and I was determined to build a perpetual motion machine. Well, I guess I'll spoil this part of the story. It's not possible to do that. I read that in a textbook somewhere, but I was like, I don't want to just take their word for it. I actually want to figure this out for myself and actually try to build one of these things. I tried for many years, and finally I got to physics in high school, and I'm super excited to take physics. And I tell you this story because this is one of the ways that I really learned this class really well. Is every single topic that we would study, I would take that and try to apply to this and say, how could this possibly help me put this together? Or is physics completely self-consistent? Or is what we're learning this week consistent with last week? Is some kind of loophole here or there? And that really, really helped me learn the material. Remember yesterday, one of the things I talked about was you guys figuring out what your own interests are. And everybody's application to this class is going to be completely different, right? We've got 30 different life stories in here. So what you do with this, yeah, be thinking about that over the course of the year. Momentum. When we get to momentum is anything that involves collisions. You want to use a framework, something like this. Okay. So bouncy balls. Hey, some kind of collision going on there. Would it be possible? Let's say you go to a big box store, walk into the lobby, pop a quarter in one of those quarter machines, get the world's bounciest bouncy ball. Okay? Guess it's meter stick. It's a little bit more than 3 feet, 1 meter. Okay? In the metric system. So could I take the world's bounciest bouncy ball, drop it for 1 meter, and maybe it would bounce higher than a meter? Would that be possible? Huh. Tell you what, if that were, that kind of makes me think somewhat of that hydraulic jump. I mean, if something could ever bounce back higher than it was dropped from, then it would have some good volume distance to get back to the original point that you can capture that energy. So, it seems like no, because that would imply a perpetual motion machine, possibly, right? But I wonder, maybe within this specific framework, is there maybe some way to quantify bounciness? The word that's called coefficient of restitution. I wonder what equations go with that, how that works. Ooh, this one. You guys ever play billiards, like pool? Right. Once you set that cue ball in motion, so you strike with the stick, right, and that cue ball, that white ball, starts going in motion. Do you think that for the next few seconds after that, everything that's about to happen is determinable? It's all going to happen, right? So wherever the other balls are, if the cue ball strikes the 7 at such and such angle, which strikes the 2, which sends it to the corner pocket, right? That's all predetermined at some point, right? Like after the cue ball's left your pull stick. Now, this has some pretty deep implications. It's related to philosophy called determinism. Right? You guys ever hear of determinism? So, if you take this model to its logical conclusion, you can say, well, isn't everything in the universe made out of physical stuff, right? Including us, including all the matter that we're made out of, right? Physics drives chemistry, foundation for biology, and biology, well, we got, these neurochemical reactions going on that tell us, when to be tired, when to be hungry. Fundamentally, it's all made out of physical stuff, right? Like particles. Right? If you had enough information about the universe, let's say you knew the position and velocity and mass of every single particle in the universe, is there enough information lying around there where everything is determinable, what's going to happen? Like you could predict, next year there's going to be exactly, X many number of hurricanes, right? And getting back to, say, like biology and like neurochemistry, if your brain is tied into physical systems, does that mean that your own decisions are in a certain way deterministic? Okay, so if you, are you like preordained to commit like some crime like 20 years from now, right? Do you have any control over that? Maybe in a way this relates to, you guys know, we've been doing this like 1 minute meditation in the morning, right? That might actually be that could actually be a pretty good exercise. Because one thing you can do with meditation is just focus on your thoughts from like a third person point of view. Maybe if you have any free will, then maybe that's the most you can get from it. There's a kind of eerie experiments into free will too, but it'll take it about this day. Okay. Now we'll also talk about quantum mechanics, which is gives maybe like a counter example to that. Gives a different set of laws to get down slow enough. Okay. Rotational motion. Got a lot of fun questions here. How much time I got? That's 3, 4, 3, 14. Okay, got half an hour. We're doing all right. Every single hurricane that passes over Florida always spins in the same way, always going counterclockwise from the top. I wonder why that is. Why do hurricanes form at all? And then why do they all spin in the same direction? Huh, what's that related to? Or here's another rotational question. Might be wondering why this one's rotational, but it is. Well, good framework to approach this next question. Okay. You guys ever tried to balance? Like I got a couple of tightrope walkers here. But like a beam or something. You guys ever hold out your hands as you try and balance, right? Like the guy on the left is, and that lady on the right, she's too, got like a whole pole, right? So I guess that's pretty helpful to keep it balanced, right? But what's the physical difference? Right? Like if you hold your hands down by your side versus if you hold your hands out, are you changing your mass? Like the amount of battery you have or the inertia you have to resist and change motion? No. Are you changing your weight? Right? Like Earth's gravity pull on you? No. Are you changing your center of gravity? If I hold my hands down, it's like right here. If I hold my hands out, same spot. Huh, so that didn't change either. But something must be physically changed. And how does that explain how it makes it easier to balance? Huh. You guys ever tried to do this off screen here? You guys ever tried to balance a pen or a pencil in your hand on a finger? It's like near impossible, right? You guys ever done that with a meter stick? Do this all day. Okay. Huh. Wonder if that's related to that. Glorification. Ooh. I bet some of you guys know what that building on the left is. What's that building on the left? That is the Burj Khalifa over in Dubai, UAE. That's the tallest building in the world. In fact, it's so tall that there's actually a difference in sunset from the bottom floor to the top floor. It's perfect for the earth. It actually makes a difference if you're observing Ramadan. There's actually different rules depending on which floor you're on when it starts to stop. No, that building is not even a kilometer tall, but I want to make believe for a moment. Let's make believe that there's a building that's 400 kilometers tall, so like hundreds of times taller than that. Okay? Somehow it doesn't collapse, yada yada. Okay? Space elevator or something. Okay? If you were on the top of that top floor, 400 kilometers tall, you would be so far up that you would actually be above the atmosphere and in a place where, well, satellites would be going around the Earth in low Earth orbit. For example, this lady in the International Space Station, this astronaut right here, okay, going in low Earth orbit. Now, does she feel any weight? Do you think she feels weight? Huh. I think she would feel weightless, right? She closes her eyes and probably super hard to tell the difference between air and deep space. And probably feels weightless, right? Right. But going back to that building, that 400 kilometer tall building, if you're staying on the top floor of that building, you look out the window, you see her fly by. It's like, oh, she's weightless. You would have about 90% of your own weight up there, about 90% of your own weight. Yeah. Hey, I have a question here. Wait, who's on there?
Yours, actually.
Oh,
It changed me today.
oh, it's what she's talking here? All right. Yeah, so your name
Mauricio.
is, okay, I think I've got one desk left. It's right behind the audio. All right, yeah, thanks. All right. So, yeah, your top, the top floor of this, oh, yeah, it's behind that lab table, okay. All right, top floor of this 400 kilometer tall building, you have about 90% of your weight. So, for example, if you weighed 100 pounds down the surface, weight about 90 pounds up there, okay, you might be able to barely tell the difference. How can that be? How can you be the same elevation as this astronaut here? And she feels weightless and you don't, huh? I bet you guys might be able to figure that out, but think about that. Remember this stuff. Okay. Another rotation question. I like this one a lot. So, say you got different rolling objects on top of this incline. Who's going to win the race as they're rolling down to the bottom? Let's say there's a little bit of friction and induces some kind of rolling motion. Okay. I will tell you that they do not tie. Somebody's going to win this race. Okay. And if there is a winner, there's going to be a first, second, third, and fourth. So none of these guys tie. Okay. I wonder if you could rank those, how you'd approach that. Maybe if you want to know what is the speed of the bottom, how could you figure that out? And what is that related to? Is it related to mass? Like if you compare the bowling ball and the tennis, or the bowling ball and the basketball, bowling ball is more massive. Does that matter? Or maybe it doesn't. A lot of times in this class, certain variables will cancel out, which means that the magnitude of those things doesn't matter. I wonder if this is one of those situations or not. I wonder if it has something to do with how the mass is distributed. Right? Like a bowling ball is solid all the way through. A basketball, the mass is pretty much like a shell, right? Like all on the surface. Huh. You know, just compare these two. And then how does that compare with cylinders? Like solid cylinders or rings? Huh. Who's going to win that race? Well, here's the question. Okay. Universal gravitation. Okay. Now, well, the order that I put these slides in is a little bit different than because this is like back to unit 3 first. What would your weight be at different places relative to the surface of the Earth? Now, all of us have spent our entire lives at the surface, so our understanding of how the world works is, well, sort of contained by that, or make that a variable in our own brains. But imagine for a moment. Let's say you start digging a tunnel. You dig all the way to the center of the Earth. let's pretend it's not a molten lava party down there. So you get to the center, and you're okay, you're not melted. And what would your weight be down there? Like, would you weigh a lot? Would you weigh very little? Maybe it's a little bit different question that might help you answer that. I'm not sure. Which way would you even be down at the center of the Earth? Like to us here versus Australians, we're upside down compared to each other, but we both, so we could be sitting room, right? What about the very center? Would your weight at the center be the same on the surface? Would it be different? Would it be more? Would it be less? And if it was different, then what if you got like halfway down, about where that guy is right there? So he's about halfway between the surface and the center. Okay. Would the difference scale linearly? Does it scale with maybe some different kind of proportion? No, what if you went the other way? What if you took off and a rocket started going up? Now, I did already tell you guys if you go about 400 kilometers up, weigh about 90% of what you do at the surface. Okay? So, seems like maybe you're getting less and less. I bet if you had a rope ladder all the way to Mars, at some point, Earth's gravity pull would become pretty negligible. Right? So, and I wonder what that relationship would look like. What if I made that into a graph? Right? Maybe your weight as a function of your position somewhere. What would it look like? Harmonic motion question. So, let's do this. Okay? You guys see that spring on the left? Okay? Let's imagine for a moment that this weight is not here. Okay, so this weight's gone. Okay? And it's just a spring. It's just hanging out. It's neither stretched nor compressed. It's just a spring, right? Okay. Now let's put the weight back on. So now the weight's clumped. It's there. Now let it go, and it goes all the way as far down as it's going to stretch. That's this picture on the right. And then it's really in tension. So then it pulls back and starts oscillating like round, round, round. You guys imagine that? Right. Then maybe after 20, 30 oscillations, it settles somewhere in the middle. Okay? I wonder what that maximum stretch length is, which goes a little bit off the screen here, okay, compared to the equilibrium position. I wonder how those compare. Okay? What frameworks would you use to make sense of that, figure that out? Okay. Now, that is the last topic that you guys are going to be tested. Well, actually, if you put unit 7 as torque rotational motion. So, okay. Anyway, you guys got 7 topics to study. AP until recently had 3 more topics. Those are crossed us out. Okay. So they're not going to test you on waves, but I'll teach you guys something on this. Probably here briefly in February. If you want to take February, teach you guys a couple of other topics that you would miss otherwise. Okay. And one of them is, you guys have ever heard this? You stand out on the sidewalk, car goes by, you hear meow. You guys ever heard that? I wonder if this is maybe one of the first times in our very long history that we've ever experienced like that particular phenomenon. What is that called, by the way? It's called the what effect? Doppler effect, right? It's something with pitch shift. Right? You guys know if you're inside the car, you don't hear that. All you hear is, if you're out on the sidewalk, you hear meow, kind of pitch shift. Yeah, we have an environment where we can actually experience that and try to make sense of that. If you're an ice cream truck going by, they're playing a song, sounds super eerie, right? Because the come towards you, sounds all fun and happy, and then it goes by and like the pitch drops. It's like, in a horror show. So now that can involve maybe some kind of pitch shift with sound waves. I wonder if that applies to light waves. Okay? Light, depending on if it's a long wave, like longer, it's like our eyes tend to perceive that as closer to red, and shorter, they perceive closer to blue, right? Like, where'd you go? Violet. We can't believe that you can look up at all the galaxies in the sky and measure those shifts and use that to determine the age of the universe. You do that? You know about universe expansion, run the clock backwards? Who here happens to know trivia, how old the universe is? How old is the universe? Yep.
13.4, right?
Yeah, Eddie got that. About 13 point something billion years old. Yeah, a little bit different numbers depending on what reference you're looking at, but anywhere between 13 and 14 billion years. I think different techniques you use, but a little bit different numbers. But yeah, that's how we know that. We do that like light. Electricity. Now, when we get to electricity, I'm mostly going to focus on DC circuits. So I'll have you show you guys how to put some basic circuits together, how to measure voltage, current with a multimeter, fire things up, that sort of thing. Here's some other cool things we could do. Actually, I'll probably have you guys make a motor like a little bit different than the one on the right. Kind of similar idea. This is a very simple motor. Just have a battery, a wire, and there is a magnet down here. What that'll do is it'll take electric energy and it'll turn it into mechanical energy. A generator, on the other hand, is the exact opposite of that. Take mechanical energy, turn it into electricity, energy of that form. Actually, motor and generator could be the same device, just they're doing opposite things to each other, depending on which way the energy is flowing. Okay? And that is, oh, got a few more topics here. Okay, so these topics are not on the AP exam, but again, February, I'll try to hit these real fast. Okay. So we've got optics on the top left. You guys see some refraction going on. Stick a straw in water, it looks bent, but it's not really. What the heck is going on there? How could you maybe take that, take advantage of it, and maybe make a microscope or telescope? Engineering, talked a little bit about engineering. This is a very famous bridge. Some of you guys might know called the Tacoma Narrows Bridge. You guys video on that one day. Maybe, I guess the goal would be to not build a bridge that, this is why you're going across like, that's not a good day. Thermodynamics, so here's a early steam engine model. Talk about some kind of abstract concepts, things do like entropy, heat flow. Relativity, so I've got a picture here of a bunch of GPS satellites going around the Earth, global positioning system. I'm sure we've all used this, just like built into our phones, right? So our phones can pick up signals that are being sent by satellites, and then put two and two together, you can pinpoint exactly where you are on the surface, down to like the nearest square meter is exactly where you are, right? All these new technologies. Now, to make GPS work, the data that's involved has to be extremely precise, like space and time data. In fact, so precise that there's actually some subtle effects that you have to consider. It turns out that time ticks differently depending on your frame of reference. So the faster you move through space, the slower you move through time. Also, as you get further away from gravity fields, time speeds up. Right? It's called special and then general relativity. Einstein figured this all out about 100 years ago. And you actually need to, if you did not take relativistic effects into account, GPS would totally not work. It'd be off by like, I forget, like many kilometers every single day. Okay, so if we had never come across, relativity, theory of relativity, then maybe that's what we'd have to do is just trial and error calibrate the clocks and these satellites, and maybe really never understand why time is running at a different rate up there. But we do have theory of relativity, so before we launch the satellites up, we could pre-adjust them down on Earth. They like slow them down a little bit, so that by the time they got up there, they were actually in sync with Earth surface. And then quantum mechanics. So I think I mentioned this before, is that most of this class, like 95% of it, plus we're really going to be focused on Newtonian mechanics. This is like macroscopic level of physics. But when you get down to the atomic level, like atomic scale, weirdly enough, there's actually a different set of laws of physics that pop up. And it's really probabilistic. If you guys ever take statistics, that's the kind of thinking that you want to be in, like a probabilistic type of statistics. What you guys are seeing here is a single step experiment, a good demonstration of something called the Heisenberg uncertainty principle. And one of the biggest unsolved mysteries in the universe is how do these two different sets of laws of physics, how are they even compatible with each other? At what point, at what scale do you can change from going quantum mechanics to like classical general relativity macroscopic physics? And to figure that out, there's something called unification that might give you more insight into what's going on with the Big Bang, what's going on at the center of a black hole, where things are like really small but also very, very massive. Things like that. Okay. I do want to show you some demos that I've got on the shelf over here. Let me see, I've got 15 minutes, I think. Oh, no, hold on. Yeah, about 14 minutes. Okay. I'm trying to make the best use of my time here. Okay, so hang tight on this. Okay, we're gonna come back to this real fast. Some other slides. You guys remember yesterday I gave you guys this page, summary of the topics of this class. This page got variables, what they mean, what units they're measured in, and then the AP equation bank, which is AP allows you to use on the AP exam. So as long as you know where all the formulas are and how to apply them, then you can have this in your hands on the exam. Okay. Now, I'll tell you what. If you go to, I'm going to show you exactly where this is. Not there. Okay. You guys remember I gave you guys some Google Classroom links? There's a new one that I'm adding to you right now. There's the old one from last year. If you go to, for you guys, it's weeks 13, 14 review. Right now, I took a ton of materials here, a couple weeks. Okay? So it's kind of near the bottom. There's a video called AP Physics 1 Review Recut. Okay, see that right there? It's something like 20, 30 minutes long. If you click on that, then I will go over all these pages. And I do recommend you do that. So you guys are using your planners. Okay? This first week, I always like to uh, wind up in this class with some folks like stage, throw a bunch of questions to you guys. So you guys have some time. Like as this class goes on, it's gonna get more intense. Like the workload's gonna get a little bit more. So right now, I think you guys have a good opportunity. So go ahead and put that in your planner. Just go find that review video and watch that. Okay. I'll tell you guys all about this class. And then as we go on, let's see other things. Okay, so some AP metrics. Here's a bunch of different AP exams. And here's the scores people got on them. Now this is, I think, national data, maybe worldwide data. And so 1 and 2 failing are in red and pink, and then passing is yellow and the green colors, like 3, 4, and 5. Okay? You guys see what the hardest exam is by passing metrics, right? It's this class right here that you're sitting in right now. So physics 1. Okay, so that's it. So just so you know, that's about a 40% pass rate. Okay. How about my last day class has been teacher's class for 3 years now. So 2019, that was the first year I taught it. Had one student get a 5, and then you see the distribution of scores. At 2020, it looks like this, and 2021, oh man, it got cut off. But this last year, I did have 3 students get 5, which would be really awesome. Okay? Oh, on the far right of the screen, you see a pie chart with percent passing. So last couple of years, I've had 40% of the students pass. Okay? So just so you know, what you're in and up against this is a really tough exam, but I think if you really enjoy this topic, hopefully you enjoyed this questions you've gone over. Think about those. You work hard and apply the framework to each of these topics that we talked about. Yeah, if you like solving puzzles, then you'll be all right. Okay. You're allowed to use pretty much any calculator on the exam. It's not your phone, as long as it does not connect to the internet. Scientific is fine, graphing is fine. These are just a few of them, but if you have a big fancy graphing, that's perfectly fine. Okay. I do have some AP questions. I might see those for another day. But let's see. Okay, wait, go ahead and flip my screen. Right. And leave lights on. You guys want lights? You want lights? Lights. Okay. All right, so 2 things I want to do in these last about 11 minutes here. Okay. One is, I know some of you guys are probably pretty hungry for some notes. So I'll give you guys a little bit. Now, next week I want to hit topics a bit more bit harder, including trigonometry and vectors. But I want to throw at least a little bit at you guys right now, just so that you're familiar with us. Find some ideas. Okay. So let's suppose that I got a ground. Green ruler. Okay. And I've got a cart. Okay. And then I'm trying to get this cart to move. Okay. I want to pull this cart. So I'm going to stand over here, like a Jolly Green Giant. And I've got a rope attached to my cart, and I'm pulling it this way. Okay? So there's a rope, got some tension in it. Okay? And my goal is to move that cart off to the right. So I want to pull the cart off to the right. Okay? Now, pulling, when pushing or pulling is a force, right? Okay? Do you think that's a vector, kind of like those plane velocity vectors, has a direction and magnitude associated with it? Yeah, right? So I'm actually going to draw this as an arrow. So this could be like an arrow vector, right? Maybe, no, I could quantify that like some number of pounds that I'm pulling, but I'm going to use newtons in this class. Maybe I'm like pulling, but for example, 100 newtons of force. I don't know, 100 newtons of force. Capital N is newtons. Won't normally spell that out, but maybe just today. Right? Now, if you look at the direction I'm pulling, though, I'm kind of pulling up and to the right. Do you think the uppish part I'm pulling has anything to do with pulling the cart across the room? No, right? Only the rightward part is actually going to move the cart. Right? If anything, the upper part, if I pull up more than the weight of the cart is pulling it down, that might actually, do you think, pull the cart off the floor? Could do that, right? Right, so I'm throwing these ideas around because we need some kind of framework to make sense of this. And I think the best framework would be to take this original 100 Newton force and to split it into component vectors, components. Look at that. So pulling up and to the right is kind of pulling up, kind of pulling to the right. Notice I made it, ooh, it's a right triangle. You guys see that right triangle right there? Right triangle? Right. And if I know not only the magnitude that I'm pulling with, but I also know the angle that I'm pulling relative to, well, I have to specify relative to what? In this case, see, it's relative to the horizontal, like relative to the floor, platform, right? If I know it's, for example, like 30 degrees or something, right? Do you think that there's enough information lying around where I could determine how hard I'm actually pulling to the right and how hard I'm actually pulling up? Huh? Probably figure that out, right? Right. So here's where, if you guys remember SOHCAHTOA, right? SOHCAHTOA. I'll put this here. Right. Mnemonic device. To help you remember what sine, cosine, and tangent stand for. Now these on your calculator. Right? This sine, cosine, tangent key. Okay. And they're functions that represent ratios. I just wanted to point this out. But okay. This is a good mnemonic device to remember. S stands for sine. Okay. And sine is, okay, here's where I'm going to do. I'm going to cheat a little bit. I'm going to throw up my notes from last class. Right. So on this triangle, because this is a right triangle, right? And remember, I've got, of course, obviously a right angle. Right? Got to have that to make this work. Right? But I could have one or two angles I could pick from, and I got to specify which of them, because once I have that established, then of the two legs, one of those legs is opposite of the angle, and one of them is adjacent to the angle. Right? You guys get that? Right. Versus if I pick the other angle, then those would be backwards, right? Something like that. Right. Right. And SOHCAHTOA is a good mnemonic device to help you remember what these ratios stand for. So sine is the ratio opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So the next two letters, OH, AH, OA, tell you what's in the numerator and denominator of those ratios, right? You guys remember that? Okay. Right. So that's probably something you learn in a trig class. How are we actually going to apply that in this class? Remember what the question was that prompted this in the first place, which is how much am I actually pulling to the right? How much am I actually pulling up? So wouldn't the question in terms of the geometric framework be more like, what are the legs of the triangle equal to? Right? What are the legs? Okay. So what I'm going to do is take those defined ratios and rearrange them a little bit and say, like, if I want the opposite side, I could just cross multiply up the hypotenuse and say the opposite side therefore is equal to hypotenuse times sine of theta, and then do the same thing for cosine, right? So the adjacent leg, if I'm solving for that, would it just be the adjacent leg is equal to hypotenuse times cosine of the angle, something like that, right? You guys got it? Right. And right, you guys good so far? I know it flashes up from last class, so fair enough. Right. But so going back to how to sketch up here, right? Let's see if we can put two and two together. Right. So if I'm pulling with 100 degrees of force at this angle, let's call this angle call it 30 degrees. Pretty good angle. Right. Yeah, that's it. Right. So do you think that how much I'm actually pulling it to the right would be equal to 100 newtons times what sine or cosine? Cosine 30 degrees, right? And then this opposite leg, how much I'm actually pulling up? Shouldn't this be equal to 100 newtons times sine of 30 degrees, right? And that's how you can split a vector into components. Right? And then with those components, you can do things later on, like add components together and say, like, okay, maybe I want to consider that this wagon actually does have a weight. Maybe it's got a frictional force on it. Maybe it's got some other forces going on it besides the tension force, right? And then how do I combine those forces to make sense of it? Well, I've got to split things into components, like as a first step, right? And then there's many steps after that. Okay? So let's get some numbers. Let's try this out. So what is 100 newtons times sine of 30? Right? That is 50 newtons. So I'm pulling with exactly 50 newtons up. That's one reason that 30 degrees is a really nice angle, because sine of 30 is always equal to exactly a half. Okay? You're going to see that a lot. Okay? One thing I really like about this calculator, scroll up, scroll over, you just pop in a cosine and everything else stays the same. 100 cosine of 30 degrees is, oh, make sure your calculator is programmed in degrees if you're working with degrees, not radians, degrees. Okay, this comes out to 86.6 newtons that way. Okay. Playing a little fast and loose with sig figs, but you guys get the idea, right? Okay. And since 30 degrees is kind of a shallow angle. I drew a little bit steeper than that, oops, but it's actually a little bit shallower than that, realistically, right? Okay. Does it kind of make sense that I'm pulling to the right more than I'm pulling up, say 86 versus 50? Okay. Kind of makes sense, right? Like that? Guys good so far? Right, so I at least wanted to plant this idea before you walked out the door. Glad I did that. Let's look at this demo table a little bit. We'll do a little bit of fun stuff before you guys take off for lunch. Okay. Any questions? Questions about vector so far? Okay. Talk more about that next week. All right, so start with this. You guys see this big contraption with, I got weights and strings and pulleys. Right? Look at this big 1 kilogram mass versus this 200 gram mass, about 0.2 kilograms. Okay? If I let both of these go, who's going to win? Who's going to pull down more? The heavy guy or the light guy? Oh, whoa. Heard some of you guys say light. So light, you are right. For the camera, let me sketch this up real fast. I've got crazy pulley system. Now some of these are double pulleys, so I can wind the string one way and then back the other way. Okay, I got 0.2 kilogram weight hanging here. Okay, and then the string is wound around and around and around and around and around again, and then back to here and it's hooked. Okay, and then I've got a 1 kilogram big guy right here. One kilogram is about 2.2 pounds, right, versus 200 grams is like 0.2 kilograms, so it's so tiny, right? Somehow, the little guy, big guy, was able to lift it. It actually went like this. What the heck? How's that working? Also notice the top 2 pulleys are fixed in place. The bottom pulley is actually movable. Let me show you guys over here. You see the top 2 is in place, bottom one's moving. Okay. Huh. I bet you could figure out the physics of what's going on there. You could effectively amplify your strength, couldn't you? You could be a little weak guy with something that's crazy heavy. Huh. And if that's true, again, if I was your age, be like, aha, this is certainly going to unlock perpetual motion somehow, right? Okay. Well, you're paying for this somehow, so you don't get something for nothing. And yeah, you think about that. Wonder how you're paying for that process. Maybe get some kind of mechanical advantage to increase your strength. Got this guy, and this is more of a thermo demo, but I do want you guys, if you guys get the opportunity to get your hands on this stuff, that's why I got it out. So if you have like 2 minutes at the end of class after a lab or something, hey, look at that hand boiler. Huh, how that works. All right, we've got a, now this one I was having trouble with last class, so let's see if I have any luck. This is the top, it's all seen top, right? Okay, does something really funny. Okay, it's gotta work a little bit. It actually flips upside down. Okay. No! So close. One more time. No, not gonna happen. I lied. We're doing on the floor. You gotta work on the floor. Yeah, see it. Oh, okay. It worked until today. Just wait for you guys. My system's gonna fail. There it is. It's upside down. Yeah, whoa, it's upside down. So, sorry if you're watching this recording. Come on. It does work. Flips upside down. I wonder how that happens. What's going on there? You guys ever play with the gyroscope? You know what? I think I've got one strung up ready to go. Do this. I get one pull with this. Okay. So, here, this thing gonna balance. It's gonna fall over, right? I mean, same principle as the top, right? Get this thing going. You know what? All right. Well, we crash landed the end of that class, but all right. Got some good stuff in the first 44 minutes. Hey, you guys have a good lunch, and I will see you tomorrow. Continue your adventure then.